All right, welcome back to our last group of topics for the course. Almost done. This is Unit 3, Topic 4, and we're into the nuclear physics now. And this is the part that people always think looks a lot like chemistry, and it does look a lot like chemistry. We're talking about reactions, we're talking about the structure of the atom, etc., etc. So there is a lot of chemistry, you could say, in this. Anyway, we're going to talk a little bit in this recording about nuclear structure and radioactive decay, the different types of decay reactions that can occur. But before we do that, just a very quick reminder to you, this topic is going to be split in two parts again, just like we've done with some of the other ones. We're going to spend the first half of this talking about the theory, and then in the second half of the recording, we'll look at some sample questions from old public exams. So let's go ahead and get started. First of all, a little bit about the structure of the nucleus itself. Because so far we've talked about only really protons in the nucleus and electrons around the nucleus. We haven't really talked about the other major particle that's inside the nucleus, and that's the neutron. Okay, now neutrons have no charge. They don't affect the chemical properties of a substance. In other words, they don't affect the things that we'll react with and stuff like that. But neutrons do affect the physical properties, such as mass, for example. Okay, the mass of an atom does depend on the charge, or sorry, the number of neutrons that are inside that nucleus. Okay, and the isotope, and that's the name we give different versions of the same element. Like, for example, hydrogen, the simplest element, one proton, has three isotopes that we know of, three known isotopes. The most common one would be this one. Okay, the most common one is this guy right here, first one. No proton, just one neutron, or sorry, no neutron, just one proton and one electron. Deuterium another isotope of hydrogen that has a neutron and a proton and an electron. We call this isotope deuterium. And when you think about it, D-E-U, that prefix usually means two of. That's basically the second one. It means there's two particles inside the nucleus. Sometimes we call it hydrogen 2, again meaning there's two particles inside the nucleus. And there's a third one called tritium, which has three particles inside the nucleus, two neutrons and a proton. Now, as we get into the larger atoms, those neutrons are very important because the neutrons provide more stability to the atom. For example, when there's only one proton, there's nothing there trying to pull the nucleus apart. But if there are two protons in the nucleus, then there's some force trying to push those apart. So that's where the neutrons come in. The neutrons are kind of like the glue that holds the nucleus together. They help make the nucleus more stable. And we'll talk more about that now in just a minute. So the only difference in these three isotopes of hydrogen essentially is the extra neutrons. The main isotope has no neutrons. The second isotope has one neutron, and the third one has two neutrons. So three different versions. They all do occur naturally in nature. But this one right here, the hydrogen 1 we call it, is the most common by far. We use a special notation to describe each one of those. Okay, we use this. This is called isotope notation, and you may have come across this in chemistry as well. The number on top we call the atomic mass number, and that tells us how many particles are inside the nucleus, or how many nucleons is the term we often use for that. Okay, it equals protons plus neutrons. The bottom number, which is the atomic number, equals just protons. That's what determines which element it is. The number of protons determines the element. If the number of protons changes, the element changes. If the number of neutrons changes, the isotope of that element changes. That's the only difference. Okay, and X, of course, is the atomic symbol. Now, when you write your public exam, you will not be given a periodic table because you will not need it. You won't have to identify, for example, that element number 17 is fluorine. You won't have to do that. Okay, you may have to figure out what that number should be, but you'll be able to do that another way, and we'll do some examples of that later. Anyway, if you want to know the number of neutrons from this symbol, all you got to do is subtract these two numbers, because remember, the bottom number is number of protons alone, and the top number is protons plus neutrons. So therefore, if you subtract those two, what's left over will be neutrons alone. All right, for example, if we looked up silver on the periodic table, we would find that its atomic number is 47. Okay, it's number 47. Therefore, it has 47 protons, and also 47 electrons, by the way, when it's a neutral atom. However, the atomic number, or the atomic mass number given on the periodic table is this, 107.8682, or 107.9, we'll call that. 107.9. Now, that's important. It's not 109. Now, why is the number 109 important? Well, silver happens to have two main isotopes. Some silver atoms have 60 neutrons, others have 62 neutrons. Okay? One has 60, one has 62. So in other words, one has 47 protons plus 60 neutrons, which is 107 as the atomic mass number. That would be this one, 10747. Okay? And then we've got another isotope has 62 neutrons, so 62 plus 47 is 109. That's 10947 silver. Two different isotopes. And we distinguish between them by writing them like that. The number on top is different, but the number on bottom is not, because the number on bottom determines the element, remember. Another way to say that, by the way, is silver hyphen 109. That's another way to write that isotope. Silver 109 or silver 107. That's another way to do it. Anyway, the number that you see on the periodic table, this guy right here, it's not 107 or 109. It's somewhere in between, but it's not exactly halfway. And the reason for that is that those two isotopes of silver do not occur in the same proportions in nature. So what we call that is a weighted average. If they were just 50-50, you could just take the straight average, add them together, and divide by 2, and you get 108. Now it's close to 108, it's about 107.9, but it's not exactly 108. And the reason for that is, we know from experimental evidence that 52% of silver atoms have 60 neutrons. In other words, they're the 107 one. And the other 48% have 62 neutrons. So that's the 109 version. So we can make what's called a weighted average. We can say 0.52, that's 52% of the 107 mass, atomic mass number, and 48%, which is 0.48 times 109, add that together, and it equals that number, which is the atomic mass number that you find when you look on a periodic table. So we call that a weighted average. Now, I've never ever seen that on the public exam, so I wouldn't worry too much about it, but I thought it was worth showing you anyway. All right, moving on. Mass, we're most used to using kilograms for mass in physics. Every calculation you've done in physics pretty much up to this point in the course was always using kilograms as your mass. Okay, and the masses of the atomic particles are actually known values. They're constants, and there they are right there. And those values are also given on the data sheet that will be provided on your public exam. Okay, and it's probably the same one your teacher has been giving you all year. At least most teachers do provide that same one, so you get used to looking at it. Okay, and if you haven't seen that before, then I have provided a copy for you in this online course. Okay, in the shell where you go in to view the recordings, There's a bunch of files there called useful files. That data sheet is one of those files that's there. Okay, so those values are on that sheet in kilograms. Okay, but kilograms are not the only unit we can use for mass. There's other units we can use. For example, there's a unit called the Unified Atomic Mass Unit, which is the letter U. And basically, the way that worked is instead of using these little tiny masses, like the mass of an electron, the mass of a neutron, like 10 to the negative 27 kilograms, that's an insanely small number. So the scientific community at the time agreed that we need a unit that's going to be a little easier to work with. So they decided to use a carbon atom as the standard. For example, a neutral carbon atom, carbon-12, okay, which has 6 protons, 6 neutrons. Let's forget about the electrons for a minute. That would be, then it was decided that that little tiny mass of the electrons would be lumped in when considered the carbon atom, but it's so small that it has almost a negligible effect anyway. Okay, the protons and neutrons, for example, are almost 2,000 times heavier than an electron. So the electrons don't add very much to the mix. Okay, so what they decided to do, since this was carbon-12 because it had 6 protons and 6 neutrons, or 12 nucleons, okay, they decided to call that 12 U's. And everything else was given a mass relative to carbon-12, including protons, neutrons, and electrons. Okay? And those values you can find in your textbook, actually, if you're interested in knowing what they are. But there is a conversion factor, and this conversion factor is actually given on your data sheet again. In fact, it says that 1 U is equal to this many kilograms. And that's pretty close to the mass of a proton or a neutron. Okay, the mass of a proton and a neutron, you remember, if we look back here, we're 1.673 times 10 to the negative 27 and 1.675 times 10 to the negative 27. So very close to that conversion. But this particular conversion factor is given if you do need to convert. Now it turns out that when we're doing energy calculations, and we'll look at some examples of that later, it's easiest to work with U's. And you'll see why in just a little bit. But sometimes you might have to work in kilograms. So there's the conversion. The third unit is an energy equivalence. This one's a little different. Einstein's expression, and this is probably the most famous equation in physics, E equals mc squared. That means that there's an equivalence between mass and energy using the speed of light. Okay? E equals mc squared means that we can write mass in an energy equivalence. And what we could do is we could find, right, 1 electron, for example, or a particle with a mass of 1 U. We could do that conversion, convert into kilograms. Then we could do E equals mc squared to get joules, change it into electron volts, change that into mega electron volts, or MeV. And what you'd end up with is 1 U would equal this many mega electron volts per C squared. Now, this part right here is an energy unit. When you add the per C squared, now it's a mass unit. It's a mass equivalence. Okay, and that one is also, this whole thing right across here, that little expression is on your data sheet, close to the bottom of the sheet. It's almost the last thing on the sheet. And that is your mass conversions between the 3 different units. Like I said, sometimes it's good to use U's, other times it's more convenient to use kilograms, other times it's more convenient to use this one. And we're going to do examples from old publics where each of those is important. So moving on. The whole thing about the nucleus is some nuclei are stable, others are unstable. Okay, the ones that are unstable will decay. So first of all, nuclear stability is more or less determined by a number of neutrons. So for the first 20 elements, for example, on the periodic table, The nucleus is pretty stable when there's one neutron for every proton, basically a 1-to-1 ratio. That makes it pretty stable. Any less, it starts to get unstable. Too many, it also gets unstable. Okay. When you go above that, from 21 to 81, 82, somewhere around that range, we need more than one neutron for every proton. Because the more protons you pack together in that nucleus, the more electrical repulsion there is. And the more glue you need to hold it together, right? The more neutrons. Remember, the neutrons are the glue. So sometimes we get up to an almost 2-to-1 ratio. And then when we get up above atomic number 82, no number of neutrons can provide enough glue, enough force to hold that nucleus together. Pretty much every element above 82 is unstable. In other words, it undergoes decay, radioactive decay, and we're going to look at the different types of reactions. Okay, all of these elements, no exceptions, above 82, they're all unstable. They eventually break down. They turn into other things in order to become more stable. So try to remember that. So one way they can become more stable is by undergoing what we call natural transmutations. And a transmutation means to transmute or change into something else. And what it changes into is another element. There are three basic types of decay, three different types of radioactive particles, if you like. There's alpha, beta, and gamma. Okay, three letters from the Greek alphabet, alpha, beta, and gamma. And by passing each of those types of radiation through a magnetic field, we can tell what some of the characteristics are. For example, we can tell if they're charged, and if so, what the charge is. Because you remember, like when an electron, for example, goes through a magnetic field, it gets deflected. So a negative charge goes one way, but the proton, the positive charge, goes the opposite way. So we can tell whether they're positive or negative like that. By how much they deflect, we can tell how much mass they have or how fast they're going. So there's a whole bunch of things we can tell by putting them through a magnetic field. So this is what was discovered. There's a thing called an alpha particle, and an alpha particle has 2 protons and 2 neutrons. Okay, that's what accounts for its mass and its charge. Its mass and its charge, remember, could be measured using that magnetic field. And the notation for that is 4-2 alpha, or because 4-2 is helium, we can write it like this. Right? A helium nucleus is essentially 2 protons and 2 neutrons. So if we take away the electrons from the helium atom, we're left with a helium nucleus, which is actually an alpha particle. It's a helium nucleus. Then there were other particles that had a negative charge, but not the same mass as an alpha particle. So obviously it wasn't really the same. But it turned out that when they measured the mass and they measured the charge, it was exactly the same as an electron. Same mass, same charge. Therefore, scientists concluded that if it walks like a duck and it quacks like a duck, it must be a duck. So in other words, if it has the mass of an electron and the charge of an electron, I guess it's an electron. So in other words, beta-negative particles are electrons. And they're usually designated with a negative sign like that. That funny-looking B, that's the beta symbol. That's the way you write a Greek letter. And the negative sign signifies that they have a negative charge. So beta-negative particles. Okay, now the negative sign is important because as a bit of time went by, they discovered other particles that were very similar. Okay, they had the positive charge of an alpha particle, but they didn't have the mass of an alpha particle. In fact, it turned out they had the same charge as a proton, but they didn't have the mass of a proton. In fact, they had the mass of an electron. So it was a brand new particle. Same mass as an electron, but the charge of a proton. So it was decided to call this particle, a positron, because it was essentially, and I hesitate to use this term, but it's essentially a positive electron. That's more or less what it is. It's kind of like a positive electron. It's just like an electron in every way except the charge is positive instead of negative. So that's a new type of particle, and we'll talk about that now in a little bit. The third type, gamma, is actually not really a particle at all. It's more a photon. It's a very short wavelength, high frequency photon. Okay, and because it's such high frequency, it has a lot of energy. It's a very energetic particle. And gamma has no charge. So if we shot those three things through a magnetic field, what would happen is this. The beta negative particle will be deflected one way, over this way, and you could determine that using your left-hand rule. Okay, you could determine that using your left-hand rule. Actually, what happens is it gets deflected upwards. The alpha particle would get deflected downwards because it has a positive charge. The gamma goes straight through. Okay, and you should remember that. You can tell by the way they're deflected exactly what each one is. Okay, and we'll look at a couple of examples of that off all public exams in a little while. Alpha and beta particles are deflected or bent in opposite directions because they have opposite charges. And that's beta negative, by the way. That would be a beta negative. Okay, and all you got to do then is use your left-hand rule to see which direction they would be deflected. And gamma rays go straight on through. They don't get deflected at all because they have no charge. They have no charge at all. All right, so there are a number of natural transmutations. So let's very quickly run through them. The first one we'll call alpha decay because it's when alpha particles are emitted. Remember, the alpha particle is that helium nucleus. So the 4,2He, that's an alpha particle. Now sometimes it'll give you this symbol. Sometimes it'll just say alpha. You need to remember that an alpha is that. That's an alpha particle. The general notation is this. When an alpha particle gets emitted, because the numbers have the balance on both sides, this plus this has to equal this. So in other words, this number here, which is what we call the daughter element, the one that forms after the reaction, has to have a number on top that is 4 less because we have to add this 4 on to get this number. And on the bottom we lose 2. So basically what we're doing is we're losing 2 protons and 2 neutrons from our nucleus. That's how a alpha decay occurs. Then there's beta negative decay. Okay, the beta negative, remember, is the electron. Now, be careful with that. Because the beta negative is an electron, it's easy to think that the electron just came from outside the nucleus somewhere and it just got spit out. That's not what happens. Beta particles are electrons, yes, but they originate in the nucleus. They're actually created in the nucleus, which is unusual because electrons are generally not in the nucleus. So what happens is this. The theory is that in beta negative decay, a neutron in the nucleus, because the nucleus is unstable, it loses a neutron by the neutron decaying into a proton. And when the neutron becomes a proton, it emits an electron. Just think about, and this is the easiest way to think about it, just think about a neutron as being a proton and an electron joined together as one. They can separate. So when it separates, we get a proton and an electron. But because the electron does not belong inside the nucleus, it gets spit out. Okay, and it gets emitted by the nucleus. The general form for that is this. Here's the beta negative particle, which is basically the symbol for an electron, 0, -1. And because of that -1, and it has to add up to this number over here, the daughter nucleus is going to add 1. Because remember, we lose a neutron, but we gain a proton. So the number on top doesn't change, because by losing a neutron and gaining a proton, the total number of neutrons plus protons remains constant. But the number of protons on the bottom must go up 1 because we gained a proton. Okay. Now the other thing that's in this reaction is a special particle called a antineutrino. Okay. So it turned out that there was a little bit of missing mass, very, very tiny, almost minuscule. In fact, so little that it almost is not worth mentioning. But there was some energy missing. So they said that there was this particle. In fact, first of all, they called it a neutrino. And the neutrino, though, didn't work quite right. The neutrino didn't work, so they had to invent another particle. Now, I shouldn't say invent, because these are actual particles that exist. But the beta-negative reaction, or decay, produces what's known as an antineutrino. Now, the only difference between a neutrino and an antineutrino is the direction that they're spinning in. That's it. Basically, it's a high-energy particle. It's one of those subatomic particles. And there's a whole bunch of other ones that have been discovered since as well, but we're not going to mention those here. Okay, so the symbol for a neutrino is kind of like a letter V. It's like a written V. And then the antineutrino is a written V with a bar over the top. The antineutrino is the one that goes in beta-negative decay. It turns out the other one goes into beta-positive decay, and we'll look at that in just a second. Now, that neutrino, it's needed to balance the energy, but we usually don't write it. Okay? It doesn't have to go there. It's kind of optional. And you wouldn't need to know that one was a neutrino and one was an antineutrino. I don't think you'll be expected to know that for a public exam. I've never seen it there anyway. That's so minuscule, so insignificant in the course that I can't see it being asked. So here's the opposite of beta-negative decay. It's beta-positive decay. Now remember, in beta-negative, a neutron decayed into a proton and emitted an electron in the process. Well, a beta-positive decay is kind of the opposite. A proton decays into a neutron and in the process emits a positron. Remember, kind of like that positive electron? It's kind of the opposite. A proton decays into a neutron, so we lose a proton, but we gain a neutron. So again, that top number is still 0, it still doesn't change. But now we're gaining a proton. So that means that, or sorry, no, we're losing a proton, not gaining one. We're losing a proton in the beta-positive decay, which means the number goes down by 1, hence the Z-1. And again, there's a neutrino here, but for simplicity's sake, we often leave that out. And we're going to look at examples of all these in the second half of this recording. Anyway, the third type of radioactive decay is the gamma decay, or gamma radiation. Now, it's easy to get confused with this one. Okay? In earlier lessons, earlier in the first half of Unit 3, we talked about how photons are emitted when electrons move from higher energy levels to lower energy levels. And that emits the energy as photons. Okay? Now, that's not how a gamma ray is produced. It is a photon, yes, but it's not produced by electrons dropping to lower energy levels. It's actually produced by a nucleus decaying to a lower energy level. In other words, the nucleus itself is releasing energy. Okay, so in other words, the nucleus is in what we call an excited state. Now the question then is, how is that possible? How is it possible for a nucleus to be in a high energy or an excited state? Well, the main way it happens is because it's a nucleus, a daughter nucleus, that just formed from a parent nucleus in another type of radioactive decay, like an alpha decay or a beta decay. Okay, and in the process, it has extra energy that it needs to get rid of. Okay, so in other words, in these processes, the alpha and beta negative and beta positive, okay, the daughter element over on the right side very quickly sheds its energy, and the gamma ray is emitted. So a lot of times, the gamma ray is simply in conjunction with the other ones at the same time. It's almost like the same step. It happens almost instantaneously to the daughter nucleus forming. Okay, but we sometimes write it separately. And you'll see examples of that as well. The final type is not really a decay, but it's another way to trigger a gamma release. Okay, another way to do that, another way to produce an excited daughter element is called electron capture. So electron capture is kind of the opposite of beta-negative decay. Instead of the nucleus spitting out an electron, somehow an electron gets absorbed by the nucleus. It ends up entering the nucleus. When that happens, it combines with a proton. Okay, it combines with a proton to form a neutron. Okay, think about the electron canceling out the proton to form a neutron, right? The positive charge and negative charge cancel, they merge into one, form a neutron. Okay, so in other words, we lose a proton, we gain a neutron. So now that the daughter nucleus has lost a proton, the bottom number is one less. Okay, it does emit a neutrino again, just like the beta positive decay, and it also emits a gamma ray at the same time. So that's just another way to produce gamma. Okay, so those are the types of nuclear decays that we're going to be looking at. So in the second half of this recording now, we're going to look at some questions that have been found on old public exams, okay, over the past number of years. So do join us for that recording. Okay, it'll be entitled Part 2, Unit 3, Topic 4,